now that we've seen a motivating example, I'd like to take a look at a very special type of series that we will examine next, which is called a geometric series. As we'll see, has a nice connection to geometry. And while the geometric visuals are very nice and enlightening for geometric series, it's also nice to just write out these series in an expanded form and in their sigma notation, because you can notice patterns that way, and sometimes it's difficult to get a really good visualization of a geometric series. So the three examples that we have right here are examples of geometric series, and before we get to a formal definition, I'd like you to pause, look at the three examples that I've provided, and think about some questions, like, what do these series have in common? Do you notice any patterns or similarities? And then lastly, one of these series is not like the other. One of these series is a divergent series, meaning that when we take a look at that limit as n is going to infinity of the nth partial sum of the series, we end up with an infinity, either a positive or a negative infinity. However, if we take a look at that limit of the sequence of partial sums and we get a finite value, then we say that this infinite series converges. So one of these series diverges. It either goes off towards infinity or negative infinity, and then two of these series converge. I'd like you to see if you can identify the series that is different, the series that diverges, even though it's a geometric series, and see if you can come up with an explanation as to why that series diverges. So pause for a moment, think about that, and when you're ready, resume the video. Now the first series is a convergent series. In fact, the first series is exactly the series that we saw in our first example, except that we've added 1 to it. Well, if this whole part of the infinite series adds up to 1, and then we add another 1 to it, this will be a convergent series. The second series is also a convergent series, and we will study it in the next set of slides. And the last series is a divergent series. Most of the time, people do not have a huge amount of difficulty picking up on the fact that the last series is divergent, because each addend is larger than the previous addend. And if we're adding infinitely many values, each of which is getting bigger and bigger and bigger and bigger, all bigger than 1, then it's pretty clear to us that that's not going to stop adding up. If we're adding infinitely many numbers larger than 1 and we keep adding them forever and ever, it's going to become infinity. And so that's very good intuition that you should keep with you as we study sequences and series. More formally, a geometric series is one where the formula for moving from one addend to the next is found by multiplying by a constant ratio. And we typically use the letter R to denote that ratio. Here, A is standing for our first addend, and notice that our second term is R times that value. Our third addend is R times the second value. Our fourth addend is R times the third value, and so on. And so if you were to write this series in its expanded form, in its sigma notation, starting at n is equal to 0, you would have a series of this form. First term times the common ratio raised to the nth power. As indicated before, geometric series are a very special type of series, partially because each of them has a beautiful representation in geometry, and you can find some really cool examples of geometric series in art, and so that's one thing that's special about them. A little more from a purist mathematical perspective, something that's nice about geometric series, which will not be the case of the series we study later on in the course, is that there is a quick and easy way to determine the exact sum of a geometric series when it does converge, and there's an equally easy way to glance at a geometric series and determine whether or not it's a convergent series. Let's finish up these videos by going back to that second example that we presented, the series 3/10 plus 3/100 plus 3/1000, and so on. Let's go back to this table where n is denoting the term we are in the sequence. Here I've chosen to start counting at first term, second term, third term, fourth term. And the real trick to figuring out what this series adds up to before we study the pattern more generally, for this particular example, the trick is to represent each of these values in their decimal equivalent. So instead of talking about 3/10 as the first term, I want to think of the first term as 0.3. That second addend, 3/100, I want to think about that as 0.03. The third addend, 0.003, and so on and so forth. And as we saw when we wrote this series in its sigma notation, each term has the form 3/10 to the nth power, and the limit of these addends, as n is approaching infinity, is 0. Each of the terms is getting smaller and smaller. No surprises there. Recall that when we're filling in the s sub n row of our table, in the first stage, the value for s sub 1 is just equal to the value for a sub 1, and then as we move across this row in the table, we obtain the next term by adding the previous s sub n value to the current a sub n value. So 0.3 plus 0.03 gives me 0.33. I then move over, add s sub 2 to a sub 3, 0.33 plus 0.003 is 0.333. I do that one more time to obtain 0.3333, and we can see that each time we progress one entry further, one stage further in the pattern, all we do is add an additional digit of 3 to the end of what we saw previously. At that point, we begin to recognize a pattern and a fraction that we're very used to converting to a decimal equivalent, which would be 1/3. Now that's the answer for this particular series. We now know what we think the answer for the sum of this series ought to be. In the next collection of videos, we will work with an entirely abstract and general geometric series and come up with a formula for what the sum of the series will be all the time, and then we'll return to this example to verify that that entirely general formula gives us the answer that we expect for this specific example.